There's a town in Prussia, I think it's in Russia now, and where Leonard Euler is from, called Königsberg. And it has a river going through it, and the river separates the town into a couple of little islands. And so to get those people to access the town, they built these bridges. Well, he was walking on the bridges one day, and he was thinking, you know, we could do something kind of interesting here. We could, I really want to, there we go. We could see if there's a way that we could go so that can the tour be made returning to the original point that crosses all the bridges. So what I'd like you to do is, let's say you started here. Can you cross all the bridges and end up on this side of the river? Go ahead and try it. See if you can do it. So we could try a couple of things. We could go here, and then that's a problem. Anybody get close? Yeah, you end up on the other side and you miss a bridge, right? Yeah, and so he was interested in this idea of vertices and edges and limitations that exist. Euler determined that such a circuit is not possible. However, it would be possible if either one of the bridges was removed or one added. Which bridge would you remove? This middle one? Okay, so if I cross those out, but wouldn't you end up on the other side? I think you'd have to take out two. You could do those two, or I was even thinking these two, and you could go back there, but I don't think one is going to do it, is it? I don't think so. And where on the diagram could you add a bridge so that you could make it back? So if we did to the bottom, so now you go here, 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 but I'd end up on the island, I think, unless I'm doing this wrong. No, you're right. Yeah, you'd be short one. I think you'd need two there as well. So this is the idea of looking at paths, and this is what I think is really interesting. Is they reduced it to this because there's the connections are the bridges, and the vertices would be the landforms. There's 1, 2, 3, 4 landforms. And yeah, so the idea there is that you could do this. Now, could you go from A and get back to A? Is it possible to get to all of the edges? Can we do it? No, right? And there's the 2 coming back again. So we're going to explore this and talk about this a little bit. Before we go any further, would you put a dot here, A? Would you show your neighbor a path you could take that will get you back to A using this one? By the way, 2 bridges, right? This is a solution. I did it wrong right off the bat. There we go. But we don't end up back at A. So that has a name. We have some names for all these. Do they end up covering all the edges? Do they meet all the vertices? Do they end up at the same spot? Do they end up at a different spot? All those are going to have names. So if you go to the next slide, you're going to see what these are called as far as terminology. The basic term for going through a graph, a path, we call a walk, and we don't call it a path. Path is going to have a different name, but a walk is just how you're going from vertice to vertice. That would be a walk. This would be a walk, V to Y. It's just whatever you want. The idea of it is to describe with symbols what's happening in the physical space. So a trail is a walk where all the edges are distinct. I like to say it this way: it covers all the edges. So let me say that one more time. A trail is a walk that covers all the edges. So that was a trail that I just did. A path is just a walk where all the vertices are covered. Okay? Covers all the vertices. Paths are cool because you just want to get to the towns or get to the stores. You don't have to go to all the roads. Trails, you got to hit all the roads. Paths just have to hit all the stores. All right. So for example, in the multigraph above, you can see a trail of length 6. So let's do it. Starts at X, goes down to V, goes over to V. Then it goes to W. And then from W it goes to Y. And from Y it goes to X. And then X it goes to, did I hit Z yet? W, Y, Z, and then it goes to X, and then back to Y. We started with X, and we ended with Y. Did we hit all of the vertices? Yeah. So that sounds like it's going to be a trail, or a path, because we covered all the vertices. But did we cover all the trails, or all the edges? No, so it's not a trail. So this is an example of a the walk where the edges are distinct. Oh, that's right. You can't use it twice. So it covers edges. Maybe it doesn't cover all the edges. It just hits the edge twice. Once. Edges once. Cross that out. I'll fix that. It's not on yours? Good. And then the path, all the vertices, this doesn't cover, it hits the vertices once. That sounds right. Okay, so the edges once, vertices once. So a walk or a trail is said to be closed if the initial and final vertices are the same. So closed would be you start at V and you end up back at V. That is also called a circuit. A closed trail is called a circuit. And what's nice about a circuit is that you're ending up at the same spot you started. A cycle is a circuit with only one repeated vertex, and that's the final one. So let's do a circuit here, or a cycle. Cycle is a circuit with only one repeated vertex. So give me an example of, with this thing, of a cycle. X, XW, X, W, V, Y, and then what? Z, X. There you go. There is a cycle, and it's also a circuit. We covered those once and only once. Good. All right, so for a multigraph, the loop Z to Z is a cycle. VXV, that's a cycle. So getting used to some of the terminology here. And then we get to something a little fancier. This is an Eulerian trail. Now, it's a trail which uses every edge in the graph once. So this is where we get something that's kind of applicable. Every edge exactly once. That's what we were trying to do before. Eulerian trail. You're trying to hit every edge exactly once. No doubling up. No double back. Right? An Eulerian circuit is where you end up where? Where you start. Yeah. End where you start. Okay. And so an Eulerian, if it contains, we call it Eulerian if it's a circuit, ends up where you started. Semi-Eulerian or Eulerian trail, that's where you end up. You cover all of the edges once and only once, but you don't end up at the beginning. So tell me, is this an Eulerian trail or an Eulerian circuit? Try it. Try as hard as we can. I don't think we can make this one work. You start up here. You're always going to end up in a different spot. So you'll be leaving out one edge. Could have started here, but you know, you're going to have to double back once. So if a graph, what we can find then is if you see any of the vertices, if a graph contains any vertices of odd degree, it won't be Eulerian. So this, what's the degree of this one? 3. This one? 4, 2, 3, 4, 5, 3, and 3. Okay? So if a graph contains any vertices of odd degree, it's not Eulerian. Let's check. Let's do a basic one here. Is that going to be Eulerian? Yeah. How many degrees at each one? 2. Now, let's say that I put these two and these two. Now this is even. Is this Eulerian? This one is 3, 4, 3, and if you go boom, boom, I think you can still traverse this one, can't you? Yeah. So when we say Eulerian, okay, we hit each one each time, but it's not going to be a circuit. So the graph Eulerian refers to it being a circuit. So if you have 2 odds, are you going to be able to end up at the same spot you started? No. But that one is an Eulerian trail. But as soon as you put in an odd degree somewhere, you're not going to end up where you started. That's the problem with it. All right, so then that's one. That's going to be helpful. Connected graph. I'm going to let you look at these theorems and corollaries. They're super helpful in seeing trends, but I almost like to have you try things before and we'll go over these a little bit on Monday too. Here's what I'd like you to try for Monday. Go to the homework, and I'd like you to do 1, 1, 2. And I think that's it. We'll just stop there, okay? And so we'll do those all the way up to the purple. And then we'll save these for Monday. Okay? Circle those. Give those a try. Take a look at the terminology. Get familiar with it. And I don't want to go into all those corollaries and theorems yet because that's overkill.